So number 14, a box contains 5 tickets. 2 2s, 2 3s, and 1 4. So the box is 2, 2, 3, 3, 4. Okay? So the sum of the draws is different than the number of 4s or the number of 2s. The sum of the draw means we add them together. Okay? So the box model is just 2, 2, 3, 3, 4. That's for the sum. So letter B, what is the probability that the sum of the draws is greater than 300 with 100 draws from the box? So let's think about something first. What is the smallest possible value we could get in 100 draws? 200. 2 over and over and over and over. Is that very likely? Very unlikely. Okay. What's the highest it could be? 400. And we want the probability that the sum is greater than 300 with 100 draws from the box. So we need the average of the box. And I might as well just plug these in and do one variable stats. How come? Because I need the SD and I can't do the shortcut. Why can I not do the shortcut? I have 3 different numbers. And you can only do that with 2. So I'm going to go into my stat. And you could find the average by adding them up and dividing by 5. But you're already going to be doing one variable statistics. So you might as well just plug them all in at the same time. So 2, 2, 3, 3, 4. Yes. Definitely. Yeah, because you don't know how to do the standard deviation by hand. I never taught it to you. Well, I kind of did, but it's annoying. So now we do statistics, calculate, one variable stats. Which number is the average? X bar. So the average of the box is 2.8, and the SD of the box is 0.748. What does 0.748 mean? The numbers in the box, on average, are 0.748 units away from 2.8. Okay? So, now we need to figure out the SE and the expected value if we do 100 draws. And this is a sum. So every draw is worth 2.8, is worth 2.8 on average. So if I do 100 draws, we're going to end up with 280 as the expected value. Yes, Lizzie? So check your numbers. So one of us made a mistake. Let's see. 2, 2, 3, 3, 4. What did you type in? Put them over there. Did anybody else get anything different? For these? Oops. Okay. So the expected value is 280, and we need the SE. So the SE is going to be 0.748 times square root of 100, which is 10. So 7.48. What does this mean? If you make 100 draws from the box, you're expected to get 280 as the sum, give or take 7.5. Everybody understand how the SE works? Now, if I increase my draws, what happens to my EV? It gets bigger. If I increase my draws, what happens to the SE? Nope. It goes up, but it goes up slower than the EV, so the percentage approaches 0. And that's really something you need to understand, is drawing more times will increase my EV and increase my SE. but the SE grows slower than the EV, which is why the percentage approaches 0. Okay? Right. So the EV is the average times the draws. So as the draws get bigger, the EV gets bigger. But the SE, we'll have to put them on the posters. The SE is the SD of the box times the square root of the draws. So I'll just put them on the test. Yeah, let me. Well, the z-score equation's up there. Oh, it's in the different form? Okay. Yeah, I can give them to you. All right. And so with those two equations, do you see why the percentage goes to 0? The EV you multiply by the draws, and the SE you multiply by the square root of the draws. So the EV is growing faster than the SE. So the percentage is going down always. Okay. What are we on? Oh, we need to finish B. So now I draw my normal curve. Do I need edges? I would. 100 is kind of on the border. So there are 5 numbers in the box. Well, you did both. How close were they? Pretty close. With 100 I would do edges, but 400 or 500, and once again, you know, they're never going to be exactly the same. So you kind of just have to decide how accurate you want to be. But let's do edges. So my center line is 280, and I want from 300 to, well, right. So I want 300. Am I going right or left? Right. So if I shade to the right and I use edges, what do I type in? 299.5. So it's going to, this, right, yeah, yes. Unless, for instance, let's say that all of the numbers in the box were even, then there would be no odd numbers in the sum, right? So in that case, you'd have to go up 1 and down 1. So it just, if we were to look at just 300, then does 299 also exist? Can you get 299? Yes. So halfway between 299 and 300 would be 299.5. But if the box contained 2, 4, and 6, and my average was 280, and I wanted 300, what is the edge of the 300 column? 290. So there's a 300 and a 298. So this line here would be 299. So it just depends on what the next column is. Everything we've done, it's 0.5 up and 0.5 down. So the edges are always 0.5 up or 0.5 down. And the reason that you need edges, let's say that we only do 25 draws. Okay, you're going to get a big column in the middle, and then you're going to get a smaller column here, and then a smaller column here, and then a smaller column there. And we don't have very many columns, right? How well do the columns line up with the normal curve? There's a lot of area outside the normal curve. But if I make a lot of draws, what happens to my columns? They become really narrow. And I end up with a whole bunch of really narrow columns. So will adding up the columns be about the same as the normal curve? Yes. In fact, eventually they're so close we can't tell the difference. So here, if this was 6, if that's your middle, let's say I wanted to go from 3 to 7. What would my edges be? Well, 6, 5, 4, 3, and then I'd have another one over here, 2, 7, 8, 9. So I want to count up the 3 column, the 4 column, the 5 column, the 6 column, and the 7 column. So what is that point right there? 2.5. And what is this point here? 7.5. So, and let's say that the SE is, for instance, 2. So 2.5 divided by 2 gives me a z-score, and this is going to be negative 1.25, up until 7.5 divided by 2 gives me a z-score of 3.75. Okay? If we don't use edges, then I would use 3 and 7. So 3 divided by 2 is 1.5. So z equals negative 1.5. And 7 divided by 2 is 3.5. Okay? So, right. So this area, the top area, is going to be larger than the bottom area. Because those columns, when we don't have very many draws, the columns are really wide. Okay, but as we approach this, our SE is going to be percentage-wise smaller. And so if you do columns, you might get negative 1.25 and 3.75 if you do edges. But if you don't do edges, you might get negative 1.24 and 3.74. Are those going to be any different? No. So does that help? Yes. So the z-score, I just did the value divided by the SE. Or sorry, value minus, oh, I should have subtracted 6. Yeah. So I actually calculated those wrong. Yeah. Yeah. Yeah, these so Lizzie just pointed out these are wrong because I didn't subtract the 6. The SE. Right. Yes. So the edges are needed if the draws are small, anywhere from 1 to 100-ish. Right? So you could do edges always. So you can always do edges, but once you get more than 100 or 200, then the edges are going to be so close to the same answer that it's not going to matter. Okay? All right, so we go back here. We've decided to do edges. Nope, not there. Here. So we want to know what are the z-scores from 2. Wow. Let's try that again. 299.5 to infinity. We want the area from 299.5 to infinity. So what's the distance from here to here? And the formula is 299.5 minus 280, which is 19.5, divided by the SE, which is 7.48. So 19.5 divided by 7.48, and we get 2.6 in a z-score of 2.6. So now I want to calculate the area from 2.6 and up. So clear my draws. Yeah. Oh, good. I'm going to go to Zoom recall. Okay. So second distribution, shade norm, and we're going to go from 2.6 to 5. And that's going to give me a pretty small area. And I get 0.0046, which is almost 0.5%, right? Could we have used the table to figure this out? So if I go to 2.6 on the table, right here, 99%, 99.1 means the middle area. So if there's 99.1% in the middle, then there's 0.9% on the edges. Divide that by 2, 0.45% in the on the right edge.
Did you add that back for that right edge?
No, it's just 0.45. So about 0.5%. So the chance of, what were we doing? The chance of getting 300 or more is very, very small, 0.5%. Okay? So you understand how we got 0.45 here? So if we use the chart, from negative 2.6 to 2.6 is 99.1%. So that means that 0.9% is contained in the two edges. So the right edge is half of 0.9, which is 0.45, which with the calculator we got 0.46%, which is almost 0.5%. Okay, C. C is different. C says build a box model for the number of 2's that get drawn from the box. Ignore the of the draw. I found that yesterday and changed it. So what would the box look like if we're counting up 2's? 2 1's and 3 0's. Does everybody understand that? We have turned it into a win-lose game. You either win when a 2 shows up or you lose when it doesn't. So we convert the box into a 1-0 box. Okay. What is the chance that fewer than 152's 52's are drawn from the box in 400 draws? So the average of the box is going to be 2 divided by 5, which is 0.4. The SD of the box is 1 minus 0 times the square root of 2/5 times 3/5. So square root of 2/5 times 3/5. So 0.489. Okay. As long as you show your work, it's fine. So the expected value in 400 draws, listen up, you guys. The expected value is going to be 0.4 times 400, which is 160. Okay. So the SE is going to be 0.489 times square root of 400, 20, times the square root of the number of draws. So 0.489 times 20, because we're making 400 draws. So we times it by 20, and we get 9.79. So if we draw 400 times for this box, we expect to get 162's, give or take 10 2's. Now I draw my normal curve. Do I need edges? 400? No. Not unless you have a huge box, but we don't. The box is not that big. So the middle is 160, and I want to find smaller than 150. And you did edges and not edges. How close were they? 3% off? Really? Wow. So 150 is negative 10 divided by 9.97. So negative 10 divided by 9.79, sorry. 9.79. Negative 10 because 150 minus 160 is negative 10. Standardize that. Where did you get stuck? Where did you get stuck? What is this your question? It's in the problem. So the second B,
I was like, what is that 400?
A, B, C, B. It's B number 2. Okay, divide that, and I get negative 1.02. So I want to shade norm. Oops, I need to clear my draws. I'm going to shade norm from negative infinity to, what was it? Negative 1.02. Okay, good. And I end up with 15%. Really? Let's try it with edges. So that would be 10.5 divided by 9.79. So 10.5 divided by 9.79, and we get 1.07. So I'm going to shade norm with negative. Oops. So with the edges, we ended up with so I got 14.2. Oh, okay. That's the distance from our desired value and the expected value. 150 is 10 away from 160, and it's on the left. That's where the negative 10 comes in. Oh, it should be 9.5. You're right. Oops. That was the left bound. Thank you. So it should be 9.5. So 9.5 divided by 9.79, and then so 0.97. So negative 0.97. Maybe. So that ended up being 16.6. Well, they're pretty close. But as long as you show your work, and how accurate is this really going to be? Well, 68% of the time you're within 1 SE, so nothing's perfect. So it doesn't really matter. Okay, 15. Letter A. How big can it be? 100. How big? From 100 to 1300. So how many times do you expect a 7 to draw? So how often does 7 happen? 1/4 of the time. So in 25 draws, you would expect 25 of them. So, are we doing, for letter B, are we using the regular box or are we going to change it? If we're counting sevens, we need a 0, 1 box. So if you're counting sevens, you have 1, 1 and 3 zeros. So the expected value is 0.25 times 100 is 25 sevens. Okay. What do you expect the sum of the draws to be? Well, we need to put it into our stat. Why am I going to use stat this time? There are not 2 numbers, there are actually 4. So 1, 3, 7, and 13. Now, this box is not normally distributed. Is that okay? Yes, because the more draws we make, the sum is going to be normally distributed. And actually, the number of sevens will also be normally distributed. So we do one variable stats. And we get the average of the box is 6. And the SD of the box is 4.58. And if we do 100 draws, 6 times 100, your expected value is 600. Okay. Mm-hmm. Yeah, which you can do in your head, right? If every draw is expected to average at 6, then we can basically add up 6 100 times. Okay? And then the SE is going to be 4.58 times 10, which is the square root of 100. So 45.8. So we expect 600 plus or minus 45.8. Okay. Now we want to know how often are we expected to get more than 650? The sum, yeah. Yeah, the expected value of the original box represents the sum. The expected value of the 0, 1 box is the number of sevens, or whatever it is. Right. Yes. Okay. So how far, do we need edges? 400 draws. Or not, sorry, not 400 draws, 100 draws. With 100 draws, we should probably use edges. So which edge are we going to pick? 649.5 or 650.5? 649, because this column here, we want to include that left edge. So 649.5. How far away is 649.5 from 600? 49.5. So I take 49.5 and I divide it by the SE, 45.8, and I'm going to get something close to 1, 1.08. Now I shade norm, and I want to go from 1.08 to 5. Now, before I hit enter, what should the answer be close to, just in your head? So 68 is the middle, which means you have 32 on the edges. So about 16. The right edge should be about 16. Is it going to be bigger than 16 or smaller than 16? Bigger because we're closer to the middle. Oh, did it end up being 14? Oh, 14.8. So that 68 rule is... Oh, yeah. Yeah, it should be slightly smaller. We're beyond 1. That's right. Thanks, Jeff. I said that backwards. No, that's just the right tail. The right tail is 14.8. If we wanted to do it in our head, we would say there's 68 here, which means there's 32 here, which means there's 16, but we weren't at z equals 1. We were slightly to the right of that. Yeah. Yeah. Yep, you can always use the table, but the table just takes more work sometimes. Sometimes it doesn't. Sometimes it saves time, but most of the time it takes shade norms faster. Okay. So 16, we're just choosing one of the two outputs. Over 200,000 Utahns are employed part-time, and about 4 times as many are employed full-time. There could be. To estimate the percentage of citizens who lack health insurance, the state government wants to take a simple random sample. In each case, if all other things are similar, which is more accurate, or are they about the same? A simple random sample of 1,000 part-time employed adults and a simple random sample of about 1,000 full-time employed adults. Which one is going to be more accurate? 1 or 2? So why would you say 1? Does the number in the population affect the accuracy of our expected value? Does the number in the population, so we build a box, we say 25% of the people are this, and 75% of people, does it matter how many things are in the box? No. What matters? The number of draws. So they're the same. Right, but the amount in the box is not important. Right? The only thing that matters is the number of draws. So second one, 2, is more accurate because you have more draws. Okay? In the third one, it's going to be 2. How come? It's 2%. So what's 2% of the part-time? Knock off 2 zeros and double, you'd get 4,000 people. Okay? And then there are 800,000 adults who are employed full-time. Knock off 2 zeros and double it, you get 16,000. Now, this is kind of weird. Is 4,000 going to be very different than 8,000? Not really, because those are huge numbers. But technically, 2 is going to be more accurate. Okay, so that question is simply asking, does the amount of numbers in the box influence your predictions? And the answer is no. In fact, we've decided that some boxes are better to work with than others. Which boxes do we prefer? The smallest possible box. So if you have 10 million people in the box and you can simplify it down to 3, it makes your calculations easier and it doesn't affect your outcomes. Okay. All right, 17. In our box, we have 1, 1, 2, 2, 9. Some of these are tricky. Calculate the probability that the sum of 36 draws is less than 100. So I need the average of the box. I'm going to go in 1, 1, 2, 2, 9. Okay. And then I'm going to do one variable stat. And I get the average of the box is 3 and the SD of the box is 3.03. Okay. So what is our expected value with 100 draws? or sorry, 36 draws. Sorry, I said 100, but so 3 times 36 is 108, and that's plus or minus 3.03 times 6, square root of the draws, plus or minus 18.18. So I draw my normal curve, I put 108 in the middle, and I want to know less than 100. Should I use edges? Definitely. You definitely want edges. So am I going to use 99.5 or 100.5? 100.5. So 100.5. How far is it from 108 to 100.5? Negative 7.5. So negative 7.5 divided by the SE, 18.18, negative 0.41. So I'm going to shade norm. And what are my endpoints? So from negative 5 or negative infinity to negative 0.41. And I get, good, 34%. Right. Okay. So we're using the same box. I can keep the average in the SD. If 400 draws or sorry, 60 people make 36 draws from the box, how many of them are expected to get a sum of 101? Is that 60 important? Yes. So we will come up with a percentage, right? Whatever the percentage is, we need to times it by 60 and find out how many of those 60 people get the answer. Okay, so we'll ignore the 60 for now. So I have 108, and I want to know exactly 101. Yes, because we're still doing 36 draws. So from 100.5, well, I said 5, and I wrote 4. 100.5 to 101.5. Now, if you're looking for a single number, you use edges no matter how many draws you make, right? Even if you make 1,000,000 draws, you still use edges. Otherwise, you're going to get 2 z-scores that are the same, and that won't work. So, we know that this one is 0.41, right? Negative 0.41 from the last problem. So I just need to do, was that 6.5? Negative 6.5 divided by, what was the SE? 18.18? So negative 3.5 or 0.357. So I'll shade norm. 0.357. So we'll shade norm from negative 0.41 to negative 0.357. And that single column contains 1.9%. So good. So 1.97% of 60. So 60 times 1.97. Oops, sorry. 60 times 0.0197. So how many people are expected to get 101? One person. 1 out of 60. So the answer is 1. One person. Yep. So we expect 2% of the people to get 101, but if we only have 60 people, then 2% of 60 is just one person. It's actually 1.1 people, but we would expect one. What if it came out 1.6? Then it would be 2 people. Right. Okay, C. If 400 draws are made from the box, what is the chance that the sum is greater than 1145? So I need a new EV and a new SE. So 3 times 400 is 1200 plus or minus 3.03 times the square root of 400. We get 60.6. So draw. Right now we're drawing 400 times. So this, when I change the draws, both of those are going to get bigger. Okay, and I want to go from 1145. Do I need edges? No, not with 400 draws. And we want this area here. How far away am I from 1200? Negative, no, negative 55. So negative 55 divided by 60.6 is negative 0.907. So now I can shade norm. Yeah. So from negative 0.907 to 5. And I get, it should be bigger than 68, and it should be about 16 bigger than 68. So 81.7. Okay. B is the tricky part, but we'll have to do it again. So D, if 125 people make 100 draws from the box, how many of them do we expect to get a sum of exactly 303? Well, we changed our draws to 100. Do we have an EV for 100? Not yet. It's going to be 300 plus or minus 30.3. I times A by 100 and I times the SD by 10. Okay. And we want exactly 303. So here's 300 and here's 303. Do we need edges? Why do we need edges? Nope. Because I'm looking at a single column. You always need edges in a single column. So 302.5 to 303.5. So how far is the left edge? 2.5. And the right edge is 3.5. So 2.5 divided by 30.3 gives me 0.0825. And then 3.5 divided by 30.3 gives me a z-score of 0.115. I'm going to put that other 5 in there. Okay, clear my draws. So we are going to shade norm from 0.0825 up to 0.1155. And we get 0.013. So 1.3%. Is that my answer? No. We need to multiply that by 125. So 125 times 0.0131. And I get 1.6, which means 2. We would expect 2 people to get exactly, what was it? 125. It's just one extra step. 303. Oh, I'm looking at the wrong. Yeah, you're right. Okay, E. If 10,000 draws are made from the box, how many 2s are expected? We need a new box. The new box says we have 2 copies of 1 and, not 0, but, and 3 copies of 0. Okay? We've had this box before. Where was it? Where did we have this? So, no, should be 0.2. So we're looking at the same box as, is it 15? No, 15B, 50 only has 4. 14. Right, it's the same box as 14. So the average is 2, and the SD, what did we get for the SD? 14. 0.74. So that saves us a little bit of time.
Wait, but isn't the average?
If we're doing a 0-1 box, should be higher. Should be 0.9 something. Okay, let's figure it out. So it's going to be the square root of 2/5 times 3/5. So square root of 2/5 times 3/5. Yeah, that makes more sense. 0.498. Okay. 10,000 draws. My expected value is 2,000 plus or minus 48.9 because I multiply the SD by 100. Okay. So E is 2,000. Oh, we're done. We didn't even need. E is just 2,000. Yep. Okay, 400 draws are made from the box. What percentage of those draws are expected to contain fewer than 171s? So the expected value is going to be 80. Nope. 0.2 times 400. Well, which box do we use? If we're counting ones, we use this same box, 2 1s and 3 zeros. So the expected value is 80. Is that right?
Yep.
And 320. Okay. Something's not right. Oh, it's not 0.2, it's 0.4. There we go. So the last one was 4,000. That's my mistake. It's 0.4, not 0.2. So it's actually 160. So 160 plus or minus 0.489 times 20 is 9.78. So we have 160 here. And I want to know fewer than 170. Do I need edges? 400 draws? Nah, we're fine. So that is positive 10. Our EV is 160, so we're going to the right. So 10 over 9.78, 10 divided by... So 1.02, shade norm from negative infinity to 1.02. Yeah, we're running out of time. So 84% Where did you get stuck?
What did you get?
I got 84%. Okay, G. If 340 people each draw 100 times from the box, how many of them will get 12 nines? We need a new box. Why do I need a new box? There's only one 9. So 1, 1, and 4 zeros. So now the average of the box is 0.2. And the SD of the box is going to be even bigger. So it'll be the square root of 1/5 times 4/5. And it's going to be bigger than that 0.48. Smaller? Well, that's just the SD. Why is that? Oh, yeah. That makes sense. Because they're closer to the average than they were before. All right, so we're going to make 100 draws. So the EV is 100 plus or minus. Or sorry, the EV, I'm sorry. The EV is 20 plus or minus 4. Everybody follow that? Okay. So we want to know how many of them will get 12 nines. So this is 20. Okay. And down here at 12, we're actually going to calculate 12.5, which is 7.5 away from the EV. Negative. Negative 7.5. Divide that by 4. Negative 7.5 divided by 4. And I get a z-score of negative 1.875. Now I shade norm. From negative infinity to negative 1.875. And that spits out a percentage for me, which is is that 38030? So 0.030, which means 3%. But 3% is not my answer. 3% times 340. So 340 times 0.03, and it says 10.2. We say 10 because we're counting people. We're not counting percentages. Yes, you certainly hang on to this.